Hello, my name is Ariel. I'm a senior here at the University of Illinois at Urbana-Champaign, and I'm excited for the ACI competition.
Hi, my name is Brenda Cardona. I'm a civil engineering student of the 3+2 international program at the University of Illinois, Urbana-Champaign. This is my second semester here and the final year of my bachelor's. I am very excited to participate in the ACI Concrete Solutions competition.
Global warming and climate change, terms that have been widespread across the media. Yet what do they truly mean and how does it affect our lives? As our population has grown increasingly over the past 100 years, the planet's ability to handle all of our needs has come under stress. Since 1880, scientists have found that the average temperature of our planet has risen by around 2 degrees Fahrenheit. In the past, this change of temperature was all it took to plunge Earth into a little ice age. As can be seen, climate change can severely affect us and is a key issue we must address today. Since we have determined that global warming is in fact real, let's analyze how we got there. Carbon dioxide levels are at an all-time high today, more so than over the past 800,000 years. And it is a greenhouse gas. It absorbs and radiates heat. By increasing the amount of greenhouse gases in our atmosphere, it not only causes an energy imbalance, but it can also affect the pH of our water in the ocean and even change the air quality in certain regions. So now that we have gotten a better understanding of climate change and what it does, let's see where we can tackle the problem. In the United States, the biggest contributor of greenhouse gas emissions are the transportation, electricity, and industry sectors. These sectors not only burn a larger quantity of fossil fuels, but also generate a substantial amount of greenhouse gases. With that, cement production is currently the largest emitter of carbon dioxide worldwide, accounting for almost 8% of carbon dioxide per year.
So, let's talk about CO2 emission of cement. Cement is the largest manufactured product on Earth by mass. In fact, it is the second most used substance in the world after water. In the last 65 years, the amount of cement produced increased by almost 34-fold. Meanwhile, the population has only increased by less than 3-fold. Therefore, this growth rate is much higher than other commodities, such as steel. Ordinary Portland cement contains more than 90% Portland cement clinker, made from abundant raw material cheaply available almost everywhere. The production process involves grinding and calcining clay in limestone. The resulting intermediate material, clinker, generates on average 842 kilograms of CO2 per ton. As much as 40% of the total CO2 emissions come from fossil fuel combustion, while the remainder comes from limestone decomposition during the calcination process. For citizens in developing or low-income countries, cement production needs to increase to meet their demands for decent built environments. CO2 emissions from cement production are expected to increase by 260% between 1990 and 2050. The 450 ppm IPCC mitigation scenario would call for a 50% reduction in anthropogenic CO2 emissions by 2050. By this year, the cement industry will account for about a third of all CO2 emissions if new methods are not implemented to reduce emissions.
So let's look at the bigger picture. How can we address the global warming issue triggered by the cement and concrete production? One effective method to reduce the CO2 emission of cement is a process called carbon capturing. Capturing CO2 is one of the most cost-effective at-point sources, with prime examples such as large carbon-based energy facilities or industries with major CO2 emissions. While extracting CO2 from air is possible, the lower concentration of CO2 in air compared to combustion sources complicates the engineering and therefore makes the process more expensive. As such, carbon capture is economically more feasible when combined with a utilization process where the cheap CO2 can be used to produce high-value chemicals to offset the high costs of capture operations. CO2 can be captured directly from an industrial source such as cement kiln using a variety of technologies, including absorption, adsorption, chemical looping, membrane gas separation, or gas hydration. As of 2020, about 1,000 of global CO2 emissions have been captured by the carbon capturing process. Therefore, there is a need for cutting calcium-based cement, a key ingredient in traditional concrete, for sustainable constructions.
Cabon-Negative Concrete is a rapidly developing construction technology that involves making concrete without cement and incorporating carbon into it. In this process, cement is replaced in the concrete mix with steel slag, an industrial byproduct that contains calcium oxide. It is then mixed with water and aggregates to form precast concrete products using standard equipment. The resultant products are cured with CO2 in a specialized absorption chamber. During the carbonation process, the gas reacts with the steel slag to form stable calcium carbonates. CO2 is permanently captured and converted into these products, filling the voids of the matrix to form a dense structure and giving concrete its strength. By eliminating cement, which forms around 12% of traditional concrete, the technology reduces the carbon footprint of the material by half. This technique has been mainly used in concrete masonry units manufacturing, where it has demonstrated highly favorable results. The outcome was a 20% reduction in materials cost, a reduction in strengthening time to under 24 hours, and a 30% increase in compressive strength. If installed, this technology would reduce annual emissions of carbon dioxide by 20,000 tons per typical concrete masonry manufacturing plant. Moreover, it can remove about 2 kilograms of CO2 from each concrete masonry unit, which reduces emissions by zero. Carbon-negative technology is an environmentally viable solution within the concrete industry. However, it has some limitations that affect its application in the long term and its expansion to other areas of the construction sector. Carbon curing can only occur in a controlled environment, so it is only useful for products such as precast panels cast prior to delivery to a construction site. Consequently, it cannot be used for liquid ready-mix concrete. The supply of steel slag is yet another issue. Only around 250 million tons of that industrial byproduct are produced every year compared to 4 billion tons of cement. This means that the world's concrete needs cannot be met yearly with steel slag.